Okay. Um, the next phenomenon we'll look at teaches a wide range of lessons, and it relates to the coin flipping that you did. So when you're asked to flip a coin 100 times and make the sequence look as if it's random, almost invariably what you do won't look like random data actually looks. And correspondingly, when you actually do the coin flipping, what you get looks very different than what you generated when you tried to do it sort of looking randomly. Now I'm having my grader decide of each sheet which one was the random one and which one was the actual flipping. She hasn't completed that yet when I'm doing this, so I don't know how often she correctly identified them. But when I did this last year for 70 students, I got 67 out of 70 correct. And she's using the same basic heuristic that I used, which isn't very complex to figure out which one's the random one and which one's the real one. And here's the heuristic roughly. If there are sequences like strings of 10 heads or 10 tails in a row, if there's a few that are like 5 or more heads or 5 or more tails in a row, if that occurs a few times, or you have 2 that are 7 in a row or 1 that's 6 in a row, it's almost certainly the result of coin flipping. Whereas if the longest streak of heads or tails is 4 in a row, or maybe you just have 1 5 in a row or something like that, and it's mostly 3 in a row, then it's almost certainly generated by the person making up the numbers. And the lesson here is we tend to think that random processes are random in the short term, are random, the randomness that even small samples will reflect the randomness. But that's just not true. Random processes are random over the long haul. Only large samples reflect the randomness. So if you flip a coin once, it's not going to be half of the time heads and half of the time tails. It's just going to be one or the other. It's going to be a homogeneous sample. It's going to be all heads or all tails. If you flip it twice, you might get heads, tails, but you might get heads, head, you might get tails, tails. And the odds that you get heads, heads are pretty good. The odds that you get tails, tails are pretty good. If you flip it 3 times, the odds that you'll have all 3 heads are a little bit lower, but not much lower. Flip it 4 times, the odds are lower still that they'll all be heads, but not a whole lot lower. It's only as you flip more and more and more and more and more that the odds that you'll get a sequence that continues on being heads becomes lower and lower and lower. And if you do the coin flipping enough times, like say you did it 100 million times, well, if you did it 100 million times, you'd sometimes have a pretty improbable streak. Maybe you'd have 70 heads in a row. Again, let that sink in. If you did it 100 million times, maybe you'd get 70 heads in a row. You might get 50 heads in a row a couple of times. And the same for tails. It doesn't mean the coin is biased. It just means that when you have really big samples, even sort of improbable runs are going to occur occasionally. And even with flipping a coin 100 times or 90 times or whatever it is that I had you do it, you're probably going to get, if it's genuinely random, if you're genuinely flipping the coin, some streaks of 5, a streak of 6, a streak of 7, maybe a streak of 8, 9, or 10. And correspondingly, if you don't have any streaks like that, or you don't even have at least a few streaks of 5, you probably weren't really flipping the coin. You were probably kind of making things up. So nearly everyone keeps runs to a minimum when artificially generating a list, but nearly every list generated by that shouldn't say slipping, it should say flipping a coin has pretty long runs. Whereas large random samples typically reflect holes, small random samples don't. Nonetheless, we're tempted to think they do. This is dangerous because it leads us to draw bad inferences from small samples. So we'll, conduct a small sample. We'll see that in the small sample, some correlation holds, like, if you're an engineering major, then you have a high GPA, and we'll infer that that correlation holds for larger samples. Well, maybe it does, maybe it doesn't, but the fact that it holds in a small sample doesn't give us much reason to think that it holds in a large sample. Similarly, the fact that in a large sample, there's 50% of coin flips are heads and 50% of coin flips are tails is very weak evidence that in a small sample that will also hold. Small samples don't reflect large, but we're tempted to think they do. How to protect yourself? Well, Again, this fallacy operates via system 1. It's not something you're consciously doing, so overcoming it requires engaging system 2. How do you do that? Well, before generalizing from a sample or taking someone else's generalization from a sample seriously, be aware that people often generalize too hasty. Be especially wary of claims about probabilities that are based on just a few salient cases. Examples like this. People say, my grandfather did this and thus and such, and he lived to be 100. Therefore, doing this thus and such will lead you to live to be 100. Oh, my friend went on the keto diet, and she lost 200 pounds. So if you go on the keto diet, you'll probably lose a lot of weight. These kinds of things. Yes, those kinds of salient cases loom large in our psychology, but no, they don't provide strong evidence that some relationship actually holds. They provide maybe a basis to investigate and see, does the way your grandfather lived actually tend to lead to long life across most cases? So you might want to look into it when you learn about the person's grandfather, but you shouldn't yet think it's true. A related lesson is that you should be wary of data that fits a hypothesis too neatly. So even if a theory is true, because of noise, especially with small data sets, you shouldn't expect the data to fit the theory perfectly. Now with large, huge, enormous data sets, you might expect a fairly neat fit, but with small data sets, you shouldn't. So when you find a really neat fit between a hypothesis and a data set on a small data set, you should have sort of a flag go off in your brain and say there's something's gone wrong here. Someone's cheating. There's some. Okay, we're going to stop there for today, and next time we'll continue by talking more about how we should think about probabilities.